Hello students. So today we are going to study design of coupling. That is chapter number 2 in design of machine elements, DME subject. So first chapter is going to be covered during tutorial session. So we are going to start today second chapter, that is design of coupling. So in this chapter, design of coupling, we are going to see mainly four types of coupling. So first let's start with what is coupling and why it has been required. So generally coupling is also known as flange coupling. So flange coupling usually applies to a coupling having two separate cast iron flanges. So each flange is mounted on the shaft and keyed to it, and the face. So uh, so why a coupling is required? So shafts. This is one type of shaft, and this is another type of shaft. Now, generally, we can make the shaft as long as we required, but due to transportation inconvenience, we generally make maximum 7 meter length shafts. Now, if we want to connect this to shaft, we required some device. So that device is called coupling. So in order to have greater length, it becomes very necessary to join two or more pieces of the shaft by means of coupling. Now, shaft couplings are used in machinery for various purposes. So main purpose is that to provide the first to provide the connection of shaft of units that are manufactured separately, such as motor and generator, and to provide disconnection for repairs or alterations. The second is to provide misalignment of the shafts or to introduce mechanical flexibility. Third is to reduce the transmission of shock loads from one shaft to another. Fifth is it should have no projecting parts. So these are the various reasons that shaft couplings are used in machinery for these purposes. Now, similar reasons will be required for a requirements for good shaft coupling. So, which shaft coupling is very good? So, first is like connection. So, we need easy connect and disconnect. The easy connect for transmitting the power and disconnect for repair purposes. So second is to easy through it should transmit full power in one from one shaft to another shaft without any losses. Then it's the second is misalignment. So here it should hold the shafts in perfect alignment. Then the third is it should reduce the transmission shocks loads from one shaft to another. And it should have no projecting parts. So these are the various requirements for a good shaft coupling. Now we will see various types of shaft couplings. So what are the types of shaft couplings? So mainly there are 6 types of shaft couplings based on the alignment. So, the first group is called rigid coupling. So it is used to connect two shafts which are perfectly aligned. So first is sleeve or muff coupling. Second is clamp or split muff coupling, or you can also call it as compression coupling. And the third and the last is flange coupling. Now, the second is a flexible coupling. So, as from the name it suggests that it can be flexible, so it is used to connect two shafts having both lateral and angular misalignment. So, first here is bushed pin type, second is universal, and the third is Oldham coupling. Now, for according to our syllabus, we are going to study this three coupling of rigid coupling and also bush pin type coupling of flexible coupling. This two are not in this it is not covered in this chapter in our syllabus. So now we will see the first type of coupling, that is sleeve or muff coupling. Now uh, let me show you the diagram of sleeve and muff coupling. Now this is the simplest form of rigid coupling, and this is made up of material is cast iron Ci. It consists of a hollow cylinder whose inner diameter is same as the shaft. Now suppose this is a shaft, so this is a shaft. Now here there is a hollow cylinder, so that is called muff or sleeve coupling. Now the diameter of the shaft is small d, and the diameter of the sleeve or muff is called, we are calling it as a capital D here. Now along with this muff we are also having a key. So here it is fitted over the ends of the two shafts by means of this key. So this is fitted with the help of key. So this is one shaft and another shaft. So this two will be fitted with the help of this key. So the power transmitted from this shaft to another shaft by means of key and a sleeve, and by means of this key and muff or sleeve. So it is very necessary that all the elements must be strong enough to transmit the torque. So the key and the sleeve both should be very much strong enough. So it is so the usual proportions of the cast iron, that is sleeve, will be as follows. So this is followed, so that is capital D, the diameter of the muff should be equal to 2 times diameter of the shaft plus 13 mm, and the length should be 3.5 times d. So this is the design of the sleeve. Now if we are going to check this design with the various stresses involved, so we will see for design for the sleeve first. So let's see here, number one, design of sleeve. So suppose torque T is to be transmitted with the help of this coupling. Now tau C is the permissible shear stress of the material of the sleeve, which is cast iron. So the safe value of the shear stress for the cast iron is generally taken as 14 megapascal. Now torque T will be equal to tau by pi by 16 tau d cube. Now what diameter we are taking here is this diameter. So that is capital D raised to 4. It is diameter of the muff. As we know, it is a hollow cylinder. Muff is having hollow, so whole diameter minus the diameter of the shaft, so d raised to 4 minus d raised to 4 divided by d. So this is the formula for torque T. Now if we take d cube common, so we are left with 1 minus k raised to 4, where k will be equal to d by d, small d by capital D. Now similarly, if we design for the key, so what will be the design for the key? So the key of the coupling may be designed in the same way the width and the thickness of the coupling key. So let's say second number, design of key. So the length of the coupling key is at least equal to the length of the sleeve, uh, at least equal to length of the sleeve, that is 3.5 d. The coupling key is usually divided in two parts, so we'll divide by 2. so that the length of the key is in each shaft. So after fixing the length of the key, the induced shear stress. So now we will design for the shear stress. So this is shear and crushing stress. So see, shear and crushing stress. So for shear stress, we are taking length L into W width into uh, D by 2, that is radius. So into, so length width into radius into tau. So tau is the shear stress. Similarly, torque T will be equal to L into T by 2 into sigma C, the crushing stress into D by 2. So the depth of the keyway in each of the shafts to be connected should be exactly the same, and the diameters should also be the same. If the conditions if these conditions are not satisfied, then key will be added on one shaft to the same end and for each shaft, and there may be driven from opposite ends. Now let's see an example to get more clear idea about this. So here, as we know that as this example says, the design and make a neat dimensioned sketch of a muff coupling which is used to connect two steel shafts transmitting 40 kilowatt at 350 rpm. So power is given 40 kilowatt. So here we can write here 40 into 10 raised to 3 watt at 40 rpm. So n is given in rotations per minute. So this we can convert in uh, uh, radian per second also. So we'll see after. So we can call it as 2 pi n by 60. So we'll get this in radian per second. Now the material for the shaft, so if you want to calculate the torque which is need to be transmitted, so we will have P divided by N. So we will have the torque that is in Newton meter. So the material for the shaft and the key is plain carbon steel. So for shaft and key is plain carbon steel. So this is the carbon steel for which the allowable shear stress, the shear stress is 40 megapascal and crushing stress is 80 megapascal. The material for the muff is cast iron for which the allowable shear stress is 15 megapascal. So for a sleeve, the muff it is given cast iron, and for key and the shaft is carbon steel. So as we know that the shear stress is very less compared to carbon steel of cast iron is 15 megapascal. So first, now if we want to design for sleeve and key, first we need the diameter of the shaft. So diameter is not given here. So we need to find the diameter. So torque is given. So torque is P upon 2 pi n by 60. So 2 pi n by 60. And torque is given is equal to pi by 16 tau d cube. From this formula we can find diameter. So if we uh, so now we have P, we have N, we have tau. So tau we are using here as 40 megapascal for carbon steel. So diameter we have got is 52 to 55 mm. Now we will design for the sleeve. So for design for the for sleeve, we know that the diameter of the sleeve will be equal to 2 times diameter of the shaft plus 13. So which is equal to 2 into 55 plus 3. Now here we got a diameter of 52 mm, but we have rounded off to 55 mm. So now we will round off the diameter of the shaft, because in reality we cannot have the shaft of each and every diameter, because of standardization, few shaft diameters will be available. So we need to round off the shaft diameter, that is 55 mm. So here also the sleeve also same thing, we got 123, so we will take 125 mm. Now length of the sleeve will be 3.5 into d. So similarly here will be 192.5 into 195 mm. So the diameter of the sleeve and the length of the sleeve we have got. Now we will see for the how much shear stress is induced in this while transmitting this power. So as we know the formula, that is pi by 16 tau dq. So torque here is equal to pi by 16 tau dq. We have to find the shear stress. So torque is 1100 into 10 to 3 is equal to pi. So from where we got the torque, that is p upon 2 pi n by 60. That power and rpm were given. So pi by 16 tau and d. So capital D we have 125 mm and small d we have, that is 55 mm. So here if you use this formula, k is small d by d, so we will able to find uh, shear stress, that is 2.97 Newton per mm square. So what was the available allowable shear stress? So here allowable shear stress was 15 megapascal, and we have got around near to 3 megapascal. So this Newton per mm square also we can call it as megapascal. So therefore this torque is very much low than the allowable shear stress. Therefore this is a safe design. Now we will design for the key. So for the key we are taking width of the key is equal to 18 mm from design data book for 55 mm shaft. So we have to use your design data book, and from that we can get design width is equal to 18 mm. Now since the crushing stress of the key material, that is sigma c, where is the crushing stress? Here the crushing stress of the key material is twice the shear stress. Therefore we will use the square key, as it is double, so we will use the square key. So therefore the thickness will be equal to width will be equal to 18 mm. Now the length of the key in each shaft will be L by 2, that will be 195 divided by 2 is 97.5 mm. Now we will check this parameters with respect to shearing stress and crushing stress. So what is the formula for first shear stress? It is torque T is equal to L W tau s into d by 2. So 1100 into 10 to 3 is equal to 97.5 into 18. So L we have got here 97.5, W is 18, and tau we are going to find out, and d small d is equal to 55 divided by 2. So here tau s we have got 22.5 Newton per mm square, so which is 22.8 megapascal, so which is very much less with respect to allowable shear stress. So allowable shear stress was 40 megapascal, so it is very much less. Then now we will see crushing stress. So formula for crushing stress is torque T is equal to L length into thickness into radius, so into sigma c. So length we have 97.5, thickness is 18, and divided by 2 sigma into d by 2 raised 55 by 2. So sigma c crushing stress we got 45.6, which is less than allowable shear stress. Allowable shear stress, that is 80 megapascal. 80 megapascal. So here we have seen here it is given the allowable shear stress is 18 megapascal. So we can conclude from this that this is very safe design. So I hope you got this first coupling, that is sleeve or muff coupling. Now in the next lecture we will see clamp or compression coupling. So thank you very much.